Hello, Calculus 1 students. We are here to discuss implicit differentiation. Let's begin by considering this graph. Quite beautiful, but if you look at this graph in green, you can tell this is not the graph of a single function. In particular, there are infinitely many lines that hit this graph more than one time, and so this fails the vertical line test. Now, we might be interested in the rate of change of y with respect to x at, say, the point 2, 1, and we will calculate this, or the rate of change of y with respect to x at the point 2 minus 1. We can see those are both points on this curve. Well, here's a formula for this graph. 8y squared is 6x squared minus x to the fourth. We could solve for y in terms of x. Maybe I will make this remark over here. We would have y squared is 3 over 4 x squared minus x to the fourth over 8. And then what does that say about y? Well, plus or minus the square root of all of this. This would be a bit intricate to work with. Y is plus or minus the square root if we wanted to think about rates of change, because part of the graph is plus the square root of 3/4 x squared minus x to the fourth over 8, and part of the graph is minus the square root of exactly what I just said. So instead of working with y explicitly, today, we are going to be working with y implicitly. And so I can just say it's easier to work with y implicitly, which was how it was presented to us at the very beginning. Exactly like this. So this is a much easier way and how we can work with y implicitly and still calculate the rate of change of y with respect to x. This is implicit differentiation. Okay, so when we are given y implicitly via an equation involving both x and y, we use, well, this is the topic of today, implicit differentiation to calculate dy dx. So we will start off with an equation like this. X and y are in this equation. We differentiate both sides of the equation with respect to x. However, it's important to understand that we must think about y in terms of x, or y as a function of x. What does this mean? Well, we must use the chain rule here. So maybe I will box this in orange because it's very important. What does that say? Chain rule says you take the derivative of the outside, evaluate it at the inside, times, well, the derivative of y with respect to x, derivative of the inside function. So this is what we need to remember throughout here. Now, as an example with a concrete function, what's the derivative of cosine of x? Hopefully everyone knows this is minus sine x. However, if you want the derivative with respect to x of cosine y, well, this will be derivative of the outside, evaluated at the inside, times derivative of the inside function. So this is really what we see here in these two examples is really what we have to be careful of when we're doing implicit differentiation. Okay, so once we have differentiated both sides of the equation, left-hand side and right-hand side, then we will have some dy dx is appearing, and we can solve for dy dx. And typically, this rate of change will involve both x and y. So let's go back to what we see here. 8y squared equals 6x squared minus x to the fourth. And let's calculate dy dx. Our very first example using implicit differentiation. Okay, well, I have 16y times dy dx. This was the chain rule here. And this will equal, now differentiate the left-hand side. We have 12x minus 4x cubed. You see how I differentiated everything, left-hand side and the right-hand side of my equation, with respect to x? Well, here, what can I do? I can just divide both sides by 16y. So I am solving for dy dx here. We have dy dx is 12x minus 4x cubed over 16y. Now, I can simplify this just slightly. You notice all these coefficients are divisible by 4. So we get, divide by 4, 3x minus x cubed, and then 4y in the denominator. Okay. This is the rate of change of y with respect to x. And we can see in this very first example, it involves both x and y. Okay, that was letter A. Now, we see the picture, we will find the equation of the tangent line. And in fact, I have both of these tangent lines graphed at the point 2, 1 and at the point 2, minus 1. So what I have recopied is our rate of change of y with respect to x. Okay, well, we know the slope for this first example at 2, 1. Well, dy dx, let's see, x is 2, y is 1. So I have 6 minus 8 divided by 4. We get negative 2 over 4, or negative 1/2. And so my equation of the tangent line would be y minus 1 is negative 1/2 x minus 2. Well, if you look at the graph, you see, what do I have here? I have minus 1/2 x plus 1, and then add this 1. Okay, so y will be negative 1/2 x plus 2. You can see my intercept here, and then go down 1 and over 1, 2. And so you can see the slope is also negative 1/2. And so this purple line checks out as to what we just calculated. All right, next one. Well, once again, we just used the slope that we've calculated, dy dx. Here, x is 2, y is minus 1. And so I have 6 minus 8 over negative 4. This is positive 1/2. And I get y plus 1 is 1/2 x minus 2. This is the line in orange that we see. Once again, you can multiply through. If you want, you will have 1/2 x. It'll be minus 1 minus another 1 like this. So here's y equals mx plus b. You can see the intercept is negative 2. And here we go, over 2, up 1. Slope is 1/2. How fantastic is this? All right, let's do some more examples. Calculating dy dx. Well, maybe this first one, I'm going to make my life a little bit simpler by using a log property first. So you notice my equation. I'm not differentiating just yet. My equation is x cubed is ln x plus ln y. A product on the inside of a log turns into a sum. Here, now I'm ready to start differentiating. Okay, so I have 3x squared equals 1 over x. And then we have 1 over y times dy dx. Well, I can just subtract 1 over x from both sides. I have 3x squared minus 1 over x is 1 over y, dy dx. And now you can multiply through by y. And so I have dy dx is 3x squared y minus y divided by x. Next one. Careful here, I have a y appearing in more than one term. Moreover, when I go to differentiate 2xy, this is really product rule. I have a product of two functions, x times y. So let's get started. Okay, when we differentiate y squared, we have 2y dy dx. Then differentiate 2xy. So my first will be 2x, and my second will be y. Very nice. So I have first times the derivative of the second, dy dx, plus the second, which is y, times derivative of the first, which is 2. And this will equal 0. Now, I have differentiated both sides of my equation. The final thing is solve for dy dx. Here, you see I'm going to leave this on the left-hand side and move this part without dy dx to the right. So I'll do that now. I have negative 2y. But on the left-hand side, you can factor out dy dx. So I will have dy dx times 2y plus 2x equals this. At this point, just divide both sides of your equation by 2x plus 2y. And we have dy dx is negative 2y divided by 2y plus 2x. You see I have a 2 as every coefficient, and so I can simplify this slightly. It's minus y divided by y plus x. Very nice. Next example, I really have two choices. I could use a property of exponents and do a product rule, or I can just leave it as is and do chain rule. And I think I'll do that. So I will just work with this directly. Let's differentiate both sides of the equation. The left-hand side becomes dy dx. The right-hand side, we have e to the x plus y. Okay, that's the derivative of the outside, because I'm thinking here, this is my inside function. So derivative of the outside, evaluated at the inside, then multiply by derivative of the inside function. The derivative of x is 1. The derivative of y with respect to x, dy dx. So here's my first step. Okay, so I need to have everything with the dy dx on one side and everything without the dy dx on the other. And I'm not too far from having that. So I have a dy dx, and then I will have minus e to the x plus y dy dx. And this will just equal e to the x plus y. What I did here is you can distribute this across the sum and then subtract e to the x plus y times dy dx from both sides. Now you see my left-hand side, I am ready to factor out dy dx. So I have dy dx, 1 minus e to the x plus y equals e to the x plus y. Now I'm ready for my final answer. We just divide by 1 minus e to the x plus y. Okay, so dy dx, this equals e to the x plus y divided by 1 minus e to the x plus y. This is my final answer. Okay, let's see. This one, we see a y in multiple terms. We also, once again, have a product rule. I believe this one came off a recent final exam. Let's find the slope of the tangent line to the graph given by this equation at the point minus 1, 2. The first thing I need to do is just differentiate, and then I will evaluate dy dx at minus 1, 2. Fantastic. Well, left-hand side, the first thing you see, we have first and second. This is going to be my product rule. So I have first, and then times derivative of the second, plus we have the second times derivative of the first. So far, I've differentiated x cubed y with respect to x. Now, we have a y to the fourth. So this would be 4y cubed times dy dx. Derivative of 9 is 0. Derivative of minus 5x equals minus 5. So I have completed the step where I differentiate both the left and the right-hand sides with respect to x. Okay. So let's rearrange some things. If I factor out a dy dx, what do I have? Well, I have here x cubed, and then I have 4y cubed. So let's write this. X cubed plus 4y cubed. This part does not have a dy dx, so I need to move it to the other side of the equation. So I will have minus 5 and then minus 3x squared y. Final step, to calculate dy dx, we just divide both sides of the equation by x cubed plus 4y cubed. And so I get dy dx is minus 5 minus 3x squared y divided by x cubed plus 4y cubed. This is not my final answer because I'm looking for the slope of the tangent line at this point, minus 1, 2. So at the point minus 1, 2, well, x is minus 1, y is 2. We may evaluate. We get minus 5 minus 3 times 2 divided by minus 1 plus, well, 4 times 8 is 32. Oh, what is this? It's negative 11 divided by 31. This is the slope of the tangent line to this graph at the point minus 1, 2. My next example, I would like to calculate dy dx when x minus sine of xy equals y. So we get started by differentiating the left-hand side and the right-hand side. Well, the derivative of x is 1. Now, we're going to have to take care when we differentiate sine of xy with respect to x. So first, I see an outside function, which is sine. Derivative of sine is positive cosine. So derivative of the outside, evaluated at the inside. But then, when I go to take the derivative of the inside function, you see I have x times y. This will be product rule. Okay, so derivative of the inside function, we have first derivative of the second plus the second times derivative of the first, just like this. Now, so far I have differentiated the left-hand side. Okay, we differentiate the right-hand side, we get dy dx. At this point, I need to move everything with the dy dx to one side of the equation and everything without the dy dx to the other side of the equation. So you notice, maybe I'll leave the 1 on this side, and then I have a minus cosine xy times y. So I have minus y cosine xy. And on this side, I have a dy dx, but I also have another term. I have a minus cosine xy times x dy dx. We will add that, and I get plus x cosine xy dy dx. Okay, I really only have one more step before I'm ready to divide here. I'll just recopy this. And then we can factor out dy dx. This would be 1 plus x cosine xy. dy dx will be 1 minus y cosine xy. Then we divide by 1 plus x cosine xy. Okay, this was a fun one. A little bit involved, but it's good for us. Well, this is my last example, and we're going to go back and look at the picture here. So we will consider the ellipse, which is defined by this equation, x squared over 100 plus y squared over 25 equals 1. Well, if you want to see the picture, it is here, the beautiful ellipse. But let's go back to the question. First, we want to verify the point 8 minus 3 lies on the graph. Okay, so if you take 8 squared over 100 plus minus 3 squared over 25, I should get 1. This 8 squared is 64, so I have 64 over 100 plus 9 over 25. Common denominator here is 100, so we can multiply by 4 over 4. Now you see everything is going to be wonderful. So I get 64 plus 36 over 100, which is 1. Now, let's move on to part B. Maybe I'll just remind us the equation of the ellipse here. We want to calculate dy dx. Okay, so we have 2x over 100 plus 2y over 25 times dy dx. Don't forget y we are considering in terms of x here, chain rule. And this equals 0. So I can just subtract x over 50 from both sides. I have 2y over 25 dy dx equals minus x over 50. And one more step. We can divide both sides by 2y over 25. dy dx will equal, we have minus x over 50. Let's see, dividing by 2y over 25 is the same as multiplying by 25 over 2y. Now I can simplify this somewhat, so let's do that here. You notice 25 over 50 is the same as a half, so I get minus x divided by 4y. This is dy dx. Okay, letter C, find the equation of the tangent line to the graph of this ellipse at this point. Well, we know the slope. This will be dy dx evaluated at the point 8, minus 3. So we substitute x equals 8, y equals minus 3. We have minus 8 over 4 times minus 3. And you can see what we get here, positive 2 over 3. Here's the slope, and I have a point, and so I get y plus 3 is 2 over 3 times x minus 8. Here's an equation of the tangent line to this graph at the point 8, minus 3. Let's copy this. And we are going to go to our beautiful picture of this ellipse. So I can sketch this line. Okay, so it goes through this point right here, but then the slope is 2/3. So if I go over 3, up 2. That will be on my graph. And then go over 3, up 2. And then go down 2, over 3. Okay, that's pretty good. I have a straight line through those points. And we can see, definitely looks like a tangent line here. That was a fun exercise. So this is the end of our discussion of implicit differentiation. Thank you so much.